Hey there, and welcome. Today, we're jumping into something that sounds, well, impossible. We're going on a quest to measure one single electron. Yeah, you heard that right. This is a journey to the very edge of reality itself.
And to really get our heads around this, just think about this quote for a second. It nails the scale of what we're talking about, right? This isn't just about measuring something tiny. We're literally knocking on the door of the universe's fundamental rules.
Okay, so just how small is small? I mean, look at that number. That's the mass of an electron in kilograms. It's a number with so many zeros after the decimal point that our brains kind of just give up. That's the mountain we're trying to climb.
So, how in the world are we going to tackle this? Well, here's our game plan. We'll start by wrapping our heads around just how impossible this measurement seems. Then we'll dive into the bizarre quantum rules we have to play by. We'll check out the engineer's toolkit, uncover the secret trick that makes it all work, and then, this is the big one, figure out why this tiny little task matters so much. And finally, we'll take a peek at what's next.
All right, let's get into it. First up, the impossible measurement. We really need to grasp the sheer scale of what we're attempting here. Now, you can't just grab a smaller ruler to measure an electron. Nope, you have to play in its backyard, the quantum realm. And let me tell you, the rules there are weird. These are the invisible hurdles we're up against.
Which, brings us to the big question. What makes this so unbelievably hard? Because it's not just that it's small. There are these deep, fundamental problems that make this one of the biggest challenges in all of science. Think of these as the boss levels in our quest. You've got quantum uncertainty, which basically says you can't know everything about it at once. Then there's environmental noise. Any stray signal, any little bit of heat is like a hurricane to an electron. It gets totally lost. And then there's the weirdest one of all, measurement back action. The very act of looking at it changes it.
This is my favorite way to think about it. It's like trying to measure the temperature of a single, tiny drop of water with a red-hot thermometer. What happens? Well, the thermometer instantly boils the drop away, right? The tool you're using completely changes the thing you're trying to measure. That's exactly what happens when you try to see an electron. So, how do you measure something that doesn't want to be seen? Well, this is where we humans get clever. Physicists and engineers have come up with an incredible toolkit, a whole arsenal of weapons designed specifically to battle this quantum weirdness, and finally get the measurement we're after. So, let's look at the main tools in our arsenal. First, you've got the Single-Electron Transistor, or SET. This thing is the most sensitive charge detector you can even imagine. Then there's the Penning trap, which is this genius device that uses magnetic fields to trap a single electron so we can study it. And finally, scanning tunneling microscopy, or STM, which lets us pretty much see individual atoms and electrons on a surface. Each one is just a marvel of engineering.
But here's the catch. Those amazing tools, they're totally useless if the world around them is too loud. So to even have a chance, scientists have to create the quietest, coldest, and stillest places on Earth. We're talking about freezing everything down to almost absolute zero, building rooms that block out any stray radio waves, and putting the entire experiment on tables that can cancel out even the tiniest tremor. It's extreme.
Okay, so we've got the tools, and we've got our super quiet lab. Now, it's time for the secret weapon. We're going to focus on that first tool, the SET, because it uses this brilliant little quantum trick to count electrons, one by one. And that trick has a name, the Coulomb blockade. The best way to picture it is to imagine a tiny little island that has a strict one-person-only rule. Once one electron hops onto that island, its own electric charge acts like a bouncer, physically repelling any other electron from trying to get on. It creates this perfect, natural, one-at-a-time gate. And here's how they make it work. An electron floats up to the island, but nope, the bouncer electron blocks it. Then, the engineers apply a teeny-tiny, super precise little nudge of voltage. It's just enough to give one, and only one, new electron the ticket it needs to hop onto the island. By counting those little voltage nudges, you're literally counting individual electrons passing through. It's a perfect quantum turnstile. This is all just mind-bendingly cool. But so what? Why are we going through all this trouble just to count single electrons? Well, it turns out this isn't just some neat science trick. This is the key that unlocks some of the most revolutionary technology we can imagine. Just take a look at this. A huge chunk, 40%, goes to quantum computing. In that world, a single electron can be a qubit, a single bit of quantum information. That's the stuff that could help us design new life-saving drugs in a matter of days instead of decades. But it doesn't stop there. It's also essential for building tinier, more powerful electronics, for creating new ultra-precise standards of measurement, and of course, for just figuring out the basic rules of how our universe works. And you know what? This incredible achievement, it's not the end of the road, not even close. It's actually the starting line for the next great leap. Mastering the single electron is just step one in learning how to truly control the quantum world.
So what's just over the horizon? We're talking about building amplifiers so unbelievably sensitive, the only thing limiting them is quantum physics itself. We're figuring out how to make quantum measurements that can actually find and fix their own mistakes. And, of course, the Holy Grail, integrating all of this into quantum computers with millions of parts, not just a handful.
When you boil it all down, this entire quest is about one simple but really powerful idea. Our ability to understand the universe is tied directly to our ability to measure it. And by learning to see and control its smallest, most basic pieces, we start to unlock its biggest, most profound secrets. And that just leaves us with one final thing to think about. We've figured out how to measure a single electron. So, what's next? What's the next impossible thing to measure that seems like science fiction today, but will be the foundation for the world of tomorrow? Thanks for joining me on this one.